You feel it now, don't you? That slow, gentle sway beneath your feet, the soft vibration running through the hull like a calm heartbeat. Out there, the void stretches forever, black velvet scattered with cold, distant stars. And you're drifting straight into a quiet mystery tonight. Something subtle, something waiting at the edge of everything you've ever understood. You can sense it in the faint pull of gravity shifting around you, the lightness in your chest as the ship glides through unseen currents. Tonight is the kind of night that makes you wonder about the impossible. For a century, scientists have whispered the same question. Could space itself be hiding secret paths, invisible tunnels linking distant galaxies, wormholes, silent folds in the dark? And as you drift here, you can't help but wonder, what if one of them is closer than you think? Before we chase that idea any further, you need to look at something you usually ignore. Not the stars glowing through the viewport, not the nebulae drifting like ghostly clouds, but the thing holding all of it together: space, time, the quiet framework beneath your feet. You hear the low hum of recycled air, steady and comforting. Space-time isn't a rigid grid bends, it stretches. It ripples around every bit of mass and energy. And because it can twist and fold, maybe it hides more than it shows. Maybe there are secret corridors curling through the darkness, waiting for travelers bold enough, calm enough to drift near them. When you look out into the emptiness, you think you're seeing nothing but silence, don't you? But that silence isn't empty, it's alive. Every star, every atom, every flicker of light moves through an invisible structure, space-time, a single woven fabric connecting every moment to every location. It's not poetry, it's real, and it's everywhere, even in the quiet around you now. A soft, steady presence, the foundation of every journey you've ever taken, including this one. You can feel it, perhaps, in the faint, almost imperceptible movements of the ship as it subtly corrects its course, a gentle nudge against the unseen architecture. This framework has measurable properties, too. It possesses curvature, it dictates causal relationships. It determines precisely how objects fall, how light bends its path, and how time itself flows. And it is anything but fixed. Space-time breathes. It responds to the presence of matter and energy. It isn't like a static grid superimposed onto the universe. It is the universe itself. When a planet settles into its orbit, it doesn't just exist in a spot. It presses into this very fabric, gently distorting the behavior of space and time around it. And when that colossal body moves, the shape of space-time subtly shifts with it, like ripples spreading across a vast, invisible pond. The presence of mass shapes the environment, and in a perfect cosmic ballet, that environment then guides how mass moves in return. This graceful, silent interaction is the very foundation of what we gently experience as gravity. So, when we ponder whether wormholes could truly exist, we aren't asking if holes can be punched through nothingness. Instead, we're wondering if space-time, this truly flexible, living fabric, might be capable of twisting and shaping itself into something far more bizarre and wonderful than we've ever dared to imagine. And that profound question begins with a quiet, almost imperceptible shift in perspective. Space isn't just where things happen. It is an active, vital part of what is happening. Take a breath. Isn't that just like space, to be full of such surprises? From our serene vantage point, high above the cosmic fray, the universe appears beautifully smooth, doesn't it? Galaxies form, elegant, swirling spirals, Clusters of stars gather in delicate, web-like filaments, and light travels freely, unimpeded, through the quiet vacuum between distant suns. There's a profound sense of calmness at this cosmic scale, a silent order, an almost hypnotic serenity. But that breathtaking smoothness is only part of the story. You might need a moment to just float here, letting that stillness wash over you. Up close, things begin to subtly ripple. Every single photon, every particle of light reflecting off our hull carries momentum. Every minuscule particle tugs ever so slightly on the space around it. Even in the profound silence between galaxies, the very fabric of space-time is constantly being nudged, gently curved, and subtly stirred by the smallest presences of mass and motion. The surface may appear flawlessly smooth, but underneath, at scales far too small for our eyes to perceive, the texture might be infinitely more complex. Perhaps you can feel the ship's gentle tremor, a micro-reflection of this unseen cosmic dance. In fact, some groundbreaking theories quietly suggest that on the very tiniest scales, space-time might not be smooth at all. It could be foamy, constantly fluctuating, or even discontinuous in certain places. Imagine microstructures, transient folds, or tiny loops bubbling into and out of existence too quickly or too minutely for our instruments to ever detect. At our current level of resolution, these variations remain invisible, much like the grain of fine paper seen from across the room. Yet they could still be profoundly real. They could still quietly shape the way everything behaves, guiding unseen destinies. And that leads us to a quiet, yet utterly astonishing possibility. Perhaps space doesn't just possess a shape. Perhaps it holds hidden features, not merely graceful curves, but profound, secret connections. Not just structure, but deep, untold secrets. The modern understanding of gravity itself began with a profound transformation in how we conceptualize space. Before Einstein, gravity was merely seen as a force, a kind of invisible pull that one object exerted on another across vast emptiness. It was a remarkably useful idea, and it worked exceptionally well for charting the grand motions of planets and moons. But it left one nagging question unresolved. How could this force travel across a vacuum? How could something influence something else without any direct contact? Einstein's answer was both subtle and incredibly profound. Gravity, he proposed, wasn't a force at all. It was, quite simply, a feature of geometry. What we feel as gravity is merely the effect of moving through curved spacetime. Picture a stretched sheet of fabric, perhaps shimmering softly in the distant starlight. Now, if you place a heavy object in the center, say, a bowling ball, sinking deep, the fabric will curve. And if you then roll a small marble nearby, it will gracefully spiral inward. Not because the bowling ball is pulling asterisk on it, but because the marble is simply following the natural curve of the fabric beneath it. This, in essence, is how gravity operates in general relativity. Planets, stars, and entire galaxies all create these magnificent indentations in the very shape of spacetime. And objects move, not because they're being pulled, but because they're quite literally falling along the paths that this cosmic geometry defines. These natural paths are called geodesics, the closest thing to a straight line in a truly curved world. Light follows them, planets follow them, even time itself subtly follows them. Everything moves along these gentle curves, shaped by the graceful warping of the underlying fabric. It's not an illusion, It's not merely a model. It's the actual, tangible shape of space that governs the behavior of all matter and light. And because the shape of space affects everything, understanding what can bend, fold, or connect that shape becomes absolutely central to understanding the quiet, breathtaking possibility of wormholes. But what then shapes that geometry in the first place? Why does the universe always do this to you, offering one answer only to reveal another, deeper question? In general relativity, the curvature of space-time is determined by the stress-energy content of whatever is present. This, of course, includes mass, the hefty presence of stars and planets, but also momentum, pure energy, radiation, and even subtle pressure. Every single form of energy, every whisper of existence, has some profound influence on the shape of space, a quiet sculpting of the cosmos. No matter how subtle, a colossal star, for instance, doesn't just sit there. It profoundly warps the very fabric around it, a cosmic divot. Even a tiny asteroid, barely a shimmer in your ship's sensors, creates its own faint indentation. And yes, even the purest energy of a starlight beam contributes in its own whisper-light way. The underlying laws, Einstein's field equations, they're truly magnificent, aren't they? One side speaks of geometry, the intricate bends and curves of space and time. The other side speaks of energy, everything within this boundless universe. It's a dance, a direct conversation. The universe's contents instruct space-time on how to curve, and in return, space-time guides all matter on its journey. You feel a gentle thrum through the hull, a soft vibration mirroring this cosmic dialogue. The precise manner of this curvature, you see, depends on more than just how much is present. It's also about how it's arranged. A superdense core of a neutron star carves out an intense, deep pocket in space-time. High pressure, like the internal forces within a gas giant, can subtly twist and distort things sideways. Even a focused beam of particles zipping past your view screen right now could create tiny ripples, ephemeral shifts in the local geometry. This incredible responsiveness means space-time isn't some passive canvas upon which events unfold. No, it's an active, ever-changing entity, truly dynamic. It listens to everything within it. And in those grand, extreme scenarios, the heart of a black hole, or the very moment of the Big Bang itself, the curvature becomes so utterly intense that the familiar tapestry of reality twists into shapes beyond our easy comprehension. So, if we were ever to encounter a wormhole, it wouldn't be because space has been stretched thin or violently ripped apart. Instead, it would be because space-time itself has been elegantly folded, shaped into a kind of cosmic bridge. The first whispers of whether such a thing is even possible come from understanding these shapes in the most extreme, mind-bending situations. If space-time truly has a shape, then every single object that journeys through it is responding to that form, whether it perceives it or not. Here, in the quiet expanse of general relativity, there's no mysterious pull acting on a falling object. It's not being yanked toward, say, a planet below. No, it's simply following the most efficient, natural pathway that space-time itself provides, a route dictated by the local curves. These natural routes, these default highways of the cosmos, we call them geodesics. In the placid, unchanging realm of flat space, a geodesic is just a straight line, simple and true. But when space begins to curve, whether gently around a distant nebula or dramatically near a collapsing star, these geodesics bend right along with it. They aren't being pushed or pulled by some unseen hand. Rather, from the perspective of the object itself, its journey remains utterly straight. It feels no acceleration, no sideways force. Even a beam of starlight, eternally traveling at its unwavering pace, will trace a curving path near a massive object. It's not because the light itself is accelerating. It's simply that the very geometry it navigates has fundamentally changed. See, isn't that just like space? This elegant concept explains why orbits occur. That distant planet, softly circling its parent star, isn't being constantly yanked sideways every fleeting moment. Instead, it's serenely following a geodesic, a path that simply loops back upon itself within the gently curved spacetime around the star. The same principle applies to our own tiny satellites orbiting Earth, silently bathed in the faint glow of the console lights. They aren't battling against some invisible force called gravity. They are, in fact, falling freely through a curved environment, tracing out the most natural, effortless paths the universe permits. And this profound principle extends beyond just the motion of objects. It applies to the very flow of time itself. Imagine, if you will, that clocks run at subtly different rates in various regions of curved spacetime. A clock nestled snugly on the surface of a world, for instance, would tick ever so slightly slower than an identical clock comfortably orbiting high above it. This isn't some optical illusion. It's a tangible, measurable consequence of how time itself stretches and compresses under the silent influence of gravity. GPS satellites, in their tireless work, must constantly make corrections for this temporal drift. Otherwise, their precise signals would fall out of sync within a matter of minutes, rendering them useless. So, these geodesics aren't merely about physical movement. They encapsulate the flow of time, the behavior of light, the very rhythm of causality itself. They are, in essence, the interwoven threads along which reality gracefully moves. And when our minds begin to drift toward the notion of wormholes, we're contemplating an even stranger, more breathtaking possibility. Could the innate shape of spacetime allow two separate geodesics, two seemingly distinct paths, to unexpectedly converge somewhere far, far away? Could there exist a hidden connection, entirely imperceptible from the outside, yet utterly real and traversable from within? This leads us to one of the most compelling ideas in all of physics: the possibility that space might be multiply connected. Instead of being the smooth, continuous expanse we intuitively expect, space might contain secret, unseen links, places where two incredibly distant regions are, in fact, directly adjacent when viewed from a different perspective. Picture this: you take a sheet of paper, perfectly flat, and fold it so that 2 points, once miles apart on its surface, now gently touch. If you were an ant, diligently crawling only on the paper's face, the journey from one point to the other would still be lengthy, time-consuming. But in the third dimension, the one you use to fold it, those 2 points are already side by side, a mere touch away. Wormholes are much like that, but woven into the fabric of space-time itself. They aren't tunnels carved out of ordinary matter. They are connections between regions of space, made possible by the way space-time curves and folds in dimensions beyond our immediate perception. From our vantage point, looking out through the shimmering viewport, there would be absolutely no visible sign of their existence, no gaping void, no ragged tear in the familiar starscape. But from within, the geometry would be radically, wonderfully different. true shortcut that utterly bypasses the vast, empty distances in between. If such a structure were to exist, it would remain entirely invisible to anyone who never ventured inside. From the outside, those two connected locations would appear as separate regions of the universe, exactly as far apart as our instruments would predict. Only by taking that intrepid step inside would you truly discover the astonishing truth that the immense gap has been collapsed. That two seemingly distinct places are, in reality, one. Physicists refer to this as non-trivial topology, the idea that space can possess hidden shapes, connections, or features that aren't immediately obvious from its surface. Think of a simple coffee mug and a donut. Topologically, they are identical, both possessing one hole in the grand tapestry of curved space-time. These holes might be invisible, not physical gaps in material, but intricate bends in geometry. And if such elegant folds or bridges truly exist, then the very structure of space isn't merely curved, it is connected, secretly, silently, and perhaps far more intimately than we've ever dared to imagine. You might need a moment to just float here, letting that concept settle into the recycled air of the cabin. The profound idea of a wormhole, you see, didn't begin in the wild, imaginative realms of science fiction. No, it emerged from a question, a quiet query buried deep within Albert Einstein's groundbreaking theory of general relativity. A fundamental question about how space and time behave, particularly near the extreme edge of a black hole. Back in 1935, Einstein himself, collaborating with Rosen, was meticulously studying a specific solution to his own equations, one that described the region outside a spherical mass, such as a non-rotating black hole. It's known as the Schwarzschild solution, and it revealed something utterly unexpected. The geometry of spacetime near such an object didn't just curve, it folded back on itself in a most peculiar, astonishing way. Einstein and Rosen realized that this solution subtly implied the existence of two identical copies of space, connected at a single, infinitesimally small point, a kind of shimmering cosmic bridge. To truly visualize this, you could imagine two entirely separate universes, each ... as you drift here, suspended in the gentle hum of our vessel, the quiet thrum vibrating softly through the deck beneath your feet, or perhaps through the very air around you. As gravity subtly shifts, consider the elegant whispers of geometry itself. Imagine two vast, separate regions of space, each with its own swirling nebulae, distant suns, and quiet galaxies, yet somehow joined, a narrow, almost impossibly slender connection, like a shimmering thread binding them at a single, precise point. This, my friend, is what they termed an Einstein-Rosen bridge, a theoretical marvel that wasn't some far-fetched dream from a holonovel. No, it was a direct, beautiful consequence of Einstein's own grand theory of relativity, a testament to how wild the universe truly is. This discovery, born from pure mathematics, opened a truly strange possibility. Could space, this boundless fabric we navigate, actually bend back on itself, split into distinct regions, and then reconnect through such a delicate, ethereal tunnel? You can feel the subtle drift of our ship, a gentle sway in the void, as your mind considers such a thing. Einstein, at the time, wasn't seeking shortcuts for interstellar travel or dreaming of alternate realities. His pursuit was far more fundamental, hoping this model might describe the basic particles of the universe without invoking those problematic singularities, infinitely dense points that often plague simpler black hole theories. For him, the bridge was an elegant mathematical evasion, a way to smooth out the universe's wrinkles. But as with many profound ideas, others saw something more, something profoundly evocative, a potential pathway through the very fabric of space and time. A tantalizing thought, isn't it? The console lights cast a soft, ambient glow across your face, reflecting momentarily in the vastness beyond our viewport, as if the stars themselves are listening. Yet there was always a catch, a fundamental problem with this early conceptual bridge. The math predicted it was inherently unstable. It would pinch shut, closing faster than any particle, any whisper of light could possibly cross from one side to the other. It existed only for a fleeting instant, not in the tangible flow of physical time, but purely within the abstract realm of mathematical space. A ghost of a connection, shimmering on the edge of possibility. To truly grasp this fragility, this quick disappearance, we need to peer a little deeper into the structure of what's called a Schwarzschild black hole and understand its true nature. The Schwarzschild solution is often celebrated as one of the most exquisitely simple and elegant answers derived from Einstein's complex equations. It perfectly describes a spherical object possessing only mass, no electric charge, no rotation. It's remarkably precise for modeling ordinary stars and planets, outlining their gravitational fields with stunning accuracy. And, in a quiet, almost poetic turn, it also unequivocally predicts the existence of black holes. Those terrifyingly dense regions where gravity's pull is so immensely powerful that nothing, not even the fleetest photon, can ever hope to escape its crushing embrace. A place of no return, a cosmic maw. Yet, when you scrutinize this geometry with a keen eye, with the same quiet curiosity that guides us through the void, something truly bizarre emerges. The very coordinates we use to map space and time near a black hole begin to behave in ways that defy our intuition. At a specific, critical radius, a boundary we call the event horizon, the roles of space and time seem to dramatically switch. Suddenly, inside this unseen barrier, every possible path, every direction, leads inexorably inward. You are pulled, as if by an invisible current, towards a central point, a terrifying convergence, the singularity. This is the place where the universe's curvature becomes infinite, where our most cherished physical theories simply break down, dissolving into an incomprehensible nothingness. What a thought, to have our science fail us so spectacularly. But just beyond that profound boundary, the space-time fabric remains perfectly defined, utterly logical. And here's where it gets truly fascinating. According to the mathematics, it's not just one region of space-time, it's two. The Schwarzschild solution, in its extended form, paints a picture of two separate sheets of space-time, perfectly mirrored across the black hole's event horizon. And within this extended vision, these two sheets are intrinsically connected by that bridge we spoke of earlier, a tunnel weaving through the interior, joining them seamlessly. From an external perspective, both sheets appear absolutely identical, each hosting its own version of the black hole. Yet, they are not the same physical location. They are reflections, mirror images, linked only at that deep, swirling throat. This profound connection, this Einstein-Rosen bridge, doesn't exist because some cosmic force dug a tunnel through space. Oh no, it's far more elegant than that. It exists simply because the very geometry of space-time asterisk allows asterisk for such a shape. It's a pure product of curvature, a mathematical object possessing a peculiar, almost whimsical property. It links to places that, by all conventional logic, should be utterly separate, yet aren't. Your recycled air systems hum gently in the background, a subtle reminder of our contained reality, even as we contemplate such vast cosmic impossibilities. Still, just like the initial concept Einstein first proposed, this extended structure suffers from the same fatal flaw. It collapses far too swiftly to permit anything to traverse it. A bridge in elegant theory, yes, but utterly impractical for any physical journey. But isn't that just like space? To present such a breathtaking possibility, only to snatch it away with the cold precision of mathematics. The idea, however, once planted, refused to wither. It lingered in the minds of physicists who continued to probe the deepest implications of general relativity. And eventually, this persistent curiosity led to a new, more urgent question, one that echoed through the quiet halls of theoretical physics. What exactly would it take to hold such a fleeting bridge, open, to carve a stable path through the cosmic fabric? You might need a moment to just float here, letting that question truly resonate within you as the distant starlight reflects softly off the curving surfaces of our ship. If a black hole is the ultimate point of no return, a region where space-time curves so drastically inward that nothing, not even light, can ever escape its gravitational prison, then it feels almost natural to wonder, doesn't it, if there could be its perfect opposite, a region of space that can only emit, never absorb. Imagine such a place. This hypothetical entity is what we call a white hole. It's another solution to Einstein's equations, a mirror image of a black hole, but running in glorious reverse. Where a black hole relentlessly pulls everything inward, a white hole powerfully pushes everything outward. Nothing can enter it. Matter and light can burst forth from its depths, but they can never, ever return. It's a cosmic fountain, an unyielding expulsion. And fascinatingly, within the extended geometry of that very same Schwarzschild solution, the one that revealed the Einstein-Rosen bridge to USA white hole, appears quite naturally as an integral part of the complete structure. Picture it. One side of this theoretical wormhole leads to a black hole, an insatiable void, while the other side opens into a white hole, a ceaseless emitter. They are not distinct entities, you see. They are merely the two opposing ends of a single complex mathematical shape. But white holes, much like a whispered secret in the quiet of deep space, are undeniably strange. No one, not ever, has observed one. They seem to flout the fundamental rules of thermodynamics, and in our tangible universe, there's no known physical process that would ever create them. They appear profoundly unstable, destined to instantly collapse at the slightest perturbation. Imagine a single photon, if it were somehow to fall into a white hole, would, in theory, cause its complete destruction. Nothing to worry about, probably. Still, even with all their quirks, as a conceptual exit point from a wormhole, the idea of a white hole holds a certain allure. If, by some impossible twist of fate, you could enter the black hole's side and somehow, impossibly, traverse the narrow throat asterisk, before asterisk it violently pinched shut, the white hole would be your spectacular emergence. An impossible escape, a one-way door from an unimaginable elsewhere. The thought is exhilarating, isn't it? The very air around us, recycled and temperature-controlled, feels charged with the sheer audacity of such an idea. But there's always that catch, that cruel mathematical reality. Even in the most optimistic scenarios, these wormholes would seal themselves almost instantly. There is simply no available time, not even a Planck moment, to cross. You can feel the subtle, almost imperceptible movement of our ship, a gentle reminder of the slow, deliberate physics of our reality. This isn't just some minor technicality, you see. It's a fundamental, deeply ingrained characteristic of the solutions themselves. Within the Einstein-Rosen bridge model, the narrow throat connecting the two space-time regions collapses utterly and completely before anything can hope to pass through. This happens because the geometry is inherently unstable, a cosmic house of cards. The precise moment any matter or energy attempts to enter to disturb its delicate structure, it profoundly warps the shape of space-time, and the bridge, like a fragile bubble, instantly collapses. This isn't a question of finding stronger materials or building at a different scale. It's intrinsically woven into the very mathematics of general relativity. The structure is impossibly delicate, relying on perfect balance, perfect symmetry, and the absolute absence of anything that might shift its weight, even infinitesimally. It's akin to trying to walk across a bridge made of pure reflections on water. The very instant you try to touch it, it simply vanishes. And so, these early, fascinating models of wormholes were ultimately dismissed, not because they were mathematically flawed, they were beautifully consistent, but because they were entirely, utterly unreachable. They existed within the equations, these shimmering pathways through the cosmos, but they offered no actual passage, no tangible crossing, no genuine hope of contact between distant regions. Yet, that audacious idea, a shortcut through the unfathomable vastness of space, refused to simply disappear into the cosmic background. The possibility lingered, like a distant star on the horizon, waiting patiently for a fresh perspective, one that wouldn't emerge from the classical physics of the past, but from the utterly strange and counterintuitive possibilities of quantum theory. And from an even more curious question than the first. What if we could somehow keep A? You drift, a quiet observer, suspended within the gentle hum of your vessel, the faint glow of console lights painting soft reflections across the viewport. The stars, countless diamonds on an endless velvet cloth, seem to beckon with their ancient, unspoken secrets. And amongst those secrets, you find yourself pondering one of the most intriguing whispers in all of cosmology, the wormhole. A shortcut, you see, a secret passage woven not through solid rock or engineered tunnels, but through the very fabric of space and time itself. Imagine taking a sheet of paper, marking to distant points, then folding it so they touch. A direct line, a tiny prick through the fold, becomes an impossibly short journey. This isn't a tunnel you carve, but a bridge formed by the universe's own pliable geometry, offering a momentary detour. What a trick, isn't it? A path that seems to defy logic from afar, yet from within could be but a breath. But, like many grand cosmic ideas, the execution proves ... tricky. The geometry required for such a cosmic bypass isn't merely complex, it's exquisitely precise. You'd need a curvature so extreme it almost hurts to imagine, yet so stable it wouldn't collapse under its own colossal weight. This connection would need to form, persist, and remain traversable, smooth enough to journey through, resisting the universe's natural inclination to pinch it shut. A brief shudder, perhaps, through the ship's hull, as if acknowledging the profound difficulty. Most theoretical wormholes, like the famous Einstein-Rosen bridge, are more concept than doorway, closing instantly or containing deadly singularities. So, the question then becomes, could nature, in its boundless creativity, ever conjure such a thing on its own? It's not an easy answer. You know, for general relativity demands conditions rarely, if ever, seen outside our most fervent imaginings. Yet, as you know, the cosmos delights in pushing boundaries. Your gaze might drift past the distant shimmer of a nebula, recalling how the universe is full of extremes, places where space-time itself twists into unimaginable densities. Consider the hearts of black holes, where gravity reigns supreme, or the moment of the Big Bang, when the entire cosmos was compressed smaller than an atom. Even within the crushing embrace of a neutron star, matter is so dense that a single cubic inch could outweigh entire mountains. If a wormhole were to form spontaneously, it would surely be in one of these places, where reality is already bent to its breaking point. Some theorists muse about the early universe, where violent fluctuations in energy might have briefly knitted together distant regions, flickering connections that winked out as quickly as they appeared. Others whisper of black holes, not as dead ends, but as hidden, sideways paths to other regions of our own universe, folded pockets of space-time tucked deep within their curvature. And then there are the quantum dreamers, who propose that reality isn't smooth at all, but rather a foamy, churning soup at its smallest scales, where tiny, undetectable wormholes are constantly forming and collapsing, too small to ever sail through, but enough to hint at a universe more tangled, more interconnected than we can readily perceive. A truly wild idea, isn't it? Still, direct evidence remains elusive. We've never observed a wormhole. We certainly don't know how to create one, and the conditions necessary seem far beyond anything we can reproduce in our most advanced labs. The question, however, remains open, quietly suspended in the shimmering web of theory. What wonders or terrors might lie on the other side? A quiet sigh might escape you, watching the slow dance of distant galaxies. For, up to this point, nearly all the wormholes we've dreamed up in our theoretical models tend to collapse. They exist, fleetingly, or not at all. The very throat of the connection pinches shut, the curvature becomes too extreme, the fragile bridge failing before it can ever truly be used. But what if a wormhole could be held open? Just what if? To achieve such a feat, you'd need something truly remarkable, something that could continuously resist the crushing, inward pull of gravity, pushing outward against space-time's relentless desire to seal the throat. Ordinary matter, sadly, simply won't do. Anything familiar, from the dust motes dancing in the ship's recycled air to the very light reflecting off your console, only adds to that inward squeeze, making the situation worse. No, what's needed is something utterly strange, something that bends space-time in the opposite direction, conjuring what we might call repulsive gravity. In the rarefied halls of theoretical physics, we label this exotic matter. This isn't just matter we haven't encountered before. It's a substance, or energy, with negative energy density, less than nothing. In the elegant equations of general relativity, negative energy doesn't pull, it pushes. A strange thought, isn't it? While mathematically permitted, its physical existence, or how one might collect and sustain it, remains one of the universe's great puzzles. Yet, if it were real, if we could somehow grasp it, it might just be the invisible scaffolding, the unseen brace, holding a wormhole's throat perpetually open, preventing its swift collapse. Without it, no known model of a traversable wormhole could survive for more than a fleeting moment. But wait, you might wonder, is this just a cosmic dream? Is there any tangible hint that negative energy is real? In fact, there might be. Even the deepest vacuum of space, seemingly empty, is never truly still. There are quantum fluctuations, tiny, unpredictable blips of energy constantly appearing and vanishing, too fleeting for the eye to catch. These fundamental wobbles are baked into the very uncertainty of quantum mechanics. Space is always subtly alive, and in certain meticulously arranged situations, these ubiquitous fluctuations can indeed produce something measurable, a very small, but undeniably real, region of negative energy. This remarkable phenomenon was first demonstrated in the 1940s, known today as the Casimir effect, a whisper of possibility, almost too faint to hear, yet profoundly real, hinting at forces we are only just beginning to comprehend. Imagine, if you will, the profound quiet of the void, disturbed only by the almost imperceptible thrum of our ship's engines, a constant, comforting whisper through the hull. You might notice the faint glow of distant console lights reflecting in your periphery as you drift, feeling the subtle give and take of recycled air. Here, in this boundless stillness, something truly peculiar occurs when certain conditions are met. Place two metallic surfaces impossibly close, just nanometers apart, within a perfect vacuum, and an unseen force gently pulls them together. It's not magnetism, not static, but a cosmic embrace born from the very fabric of space itself. Isn't that just like the universe, full of hidden nudges? This delicate attraction, a phenomenon scientists call the Casimir effect, hints at the universe's deeper, stranger mechanisms. Outside those plates, all the countless, flickering quantum energies of empty space dance freely, like an endless, silent symphony. But between them, constrained by their closeness, only certain wavelengths of these invisible oscillations are permitted to hum. This creates a subtle pressure imbalance, a tiny energetic deficit between the plates and the vast emptiness beyond. It implies a pocket of space containing, in a measurable, physical sense, less energy than what we perceive as nothing at all. A whisper of negative energy, real and detectable, briefly existing on the smallest of scales. This elusive, less-than-nothing feeling, a momentary dip in the cosmic energy budget, is our first tangible clue that what was once mere theory might actually be woven into reality. We're not talking about vast reserves of it, nor is it easy to gather, but it's a profound demonstration that the universe permits such bizarre conditions. And if that's true, even fleetingly, then perhaps, just perhaps, the fundamental ingredients for something truly extraordinary, a traversable wormhole, are already here, nestled within the very fabric of space-time. Not a figment of distant science fiction, but a potential architectural wonder awaiting discovery. It was with this quiet wonder that, in 1988, two thoughtful minds, Kip Thorne and Michael Morris, began to seriously ponder these cosmic shortcuts. Their goal wasn't to prove that wormholes existed, but to understand what kind of space-time architecture would be needed to create a gentle, traversable tunnel, one that wouldn't crush a traveler or collapse into oblivion. They asked if we could design a smooth passage through space, slow and safe, without extreme forces or disorienting time distortions, what would that look like? The answer they meticulously crafted, born from Einstein's equations, became known as the Morris-Thorne wormhole. Imagine it, a beautifully smooth, non-singular tunnel connecting to impossibly distant regions of space with no deadly event horizons to trap you. You could simply drift in, perhaps feeling a gentle shift in the ship's subtle gravity, and then drift out again. The console lights might momentarily dim, or you might feel a slight temperature change as you pass through. But here's the profound catch, the deep secret within its throat, to keep this cosmic aperture from collapsing. The design demands a specific, significant amount of negative energy density. It requires an exotic kind of matter, an unusual, unseen substance that gently yet powerfully pushes outward, holding the tunnel open against the immense gravitational forces that would otherwise pinch it shut. Space isn't being torn, it's being coaxed, shaped, and curved in a very particular, elegant way. This need for exotic matter, however, introduces a deeper philosophical ripple. It's not just about difficulty, it's about challenging the universe's most fundamental assumptions. General relativity generally presumes certain energy conditions, quiet agreements that ensure space-time behaves predictably, forbidding bizarre energy distributions and making sure cause leads to effect. The null energy condition, for instance, implies light rays will always converge under gravity's influence. But this exotic matter, by its very definition, subtly breaks these rules. It would cause light rays to spread apart, to diverge, as if gravity itself had turned gently repulsive. Such a disruption doesn't invalidate the elegant mathematics, but it does raise profound questions, doesn't it? Does nature truly permit this kind of behavior, or are these solutions merely mathematical curiosities, ultimately forbidden by principles we don't yet grasp? You might need a moment to just float here, pondering this. Some physicists suggest quantum mechanics already shows us that these energy conditions can be locally and temporarily violated, like brief flickers in the cosmic fabric. Others worry that any structure requiring such violations might be inherently unstable, unable to persist without constant, impossible input. But the truth remains. The only known way to hold a wormhole open involves something that subtly challenges the very assumptions that make our universe so comfortably predictable. We are, quite literally, far outside the world of ordinary matter, deep in the unknown. The possibility of such a stable, traversable wormhole doesn't just raise engineering questions. It opens a profoundly curious door onto time itself. Imagine the silent reflection of starlight on our hull and the subtle movement of our ship. As you consider this, if a wormhole connects to distant points in space, and if each of its mouths could move independently, then under the right gentle conditions, it might also link to different moments in time. What if one mouth remained stationary, while the other was gently accelerated to near the speed of light, then brought back again? Due to time dilation, a real effect confirmed by countless experiments, the moving mouth would have aged less than the one that stayed put. And now, the wormhole connects not just distant places, but different moments. Enter through one mouth, and you might step into the past. Exit through the other, and you could return to a future that has already unfolded. In principle, a wormhole could become a time machine, leading to what physicists call closed time-like curves, paths through space-time that eventually loop back to their own beginning. Why does the universe always do this to you, offering such mind-bending possibilities? This creates a host of paradoxes. What if you went back and changed something that prevented your own trip from occurring? To address these captivating puzzles, physicist Stephen Hawking proposed a thoughtful idea: chronology protection. The notion that the laws of physics might, in some elegant, unseen way, conspire to prevent the formation of time machines. Perhaps quantum effects would violently destabilize the wormhole just as it's about to form a time loop, or vacuum fluctuations would grow uncontrollably, like a cosmic storm. Perhaps something always intervenes, gently closing the door before time travel truly begins. We don't yet know if such protection exists, The faint hum of our life support system is a constant reminder of the known, but the universe outside continues to whisper its secrets, forever pushing us toward the edges of what we understand. As we drift here, suspended in this endless quiet, our thoughts often journey to concepts that stretch the very fabric of understanding. Imagine, if you will, a pathway through the cosmos that doesn't just bend the light from a distant star, but genuinely twists time itself. A stable wormhole, you see, isn't merely a shortcut. It's a profound rearrangement of cause and effect, making these theoretical tunnels even more bewildering than our initial imaginings. Despite the mind-bending complexities, the question persists, doesn't it? Could such an enduring passage form naturally, perhaps in the furnace of a dying star, or through the deliberate, colossal efforts of some advanced civilization? Our equations, those elegant scribbles of thought, suggest the geometry is permissible and hint at the exotic energies needed. But that's still light years from knowing if they truly exist beyond the elegant dance of mathematics. You feel the gentle thrum beneath your seat, a steady pulse of distant engines, a comforting vibration through the hull of our vessel. It's a reminder of how far our own modest technology has brought us. In nature's vast, unhurried timeline, there are so few moments where the perfect, impossible conditions for such phenomena might briefly arise. Perhaps in the early universe, that dense, swirling cauldron of primordial energy, far beyond anything we could ever hope to recreate in our most ambitious labs, tiny, ephemeral wormholes flickered into existence for fractions of a second. Some models even propose that the explosive, rapid expansion of space in its infancy could have left behind small, indelible topological defects, faint echoes of tunnels, loops, or strange connections woven into the very vacuum. These wouldn't be large enough for you to navigate, of course, but they would silently proclaim that space can indeed connect itself in the most unexpected ways. Then, we allow our minds to wander even further into the realm of truly speculative ideas. Could an ancient, incredibly advanced civilization, one that has mastered both the subtle dance of quantum mechanics and the grand waltz of general relativity, ever construct or stabilize a gateway like this? Think of the power they would wield, generating unimaginable quantities of negative energy, sculpting the very curvature of space-time with the precision of a cosmic artisan, preventing the throat of such a tunnel from collapsing back into oblivion. It's truly impossible to know for us, isn't it? Our current understanding suggests that any such endeavor would demand technologies so far beyond our wildest imaginings, a control over matter and energy on a scale we haven't even begun to comprehend. Still, the whisper of possibility keeps the brightest minds at work. You might hear the faint whir of the life support gently circulating the recycled air, a quiet counterpoint to the enormity of the void outside. Every year, new theories emerge from the quiet corners of research, proposing fresh perspectives, new stabilizing forces, or novel interpretations of quantum gravity that might allow for long-lived wormholes without defying fundamental cosmic laws. Even if we never build one, even if they remain forever out of our direct reach, their logical existence as a consequence of our deepest theories keeps the idea shimmering. It's not because we are certain they are real, but because, so far, nothing has definitively proven they are not. Isn't that just like space? Always holding on to its secrets until just the right moment. Up until now, our contemplation of wormholes has been grand, hasn't it? imagining vast high-energy structures that might stretch across nebulae or form in the fiery hearts of stars. But there's a quieter possibility, a secret whisper in the cosmic fabric itself. One that hides not in the immensity of the universe, but in its most minute, most intimate corners. To find it, we must mentally shrink, not just to the scale of atoms or their even smaller particles, but far, far beyond, to the Planck scale, the smallest meaningful measurement in all of physics. At this unimaginable level, a trillion times tinier than even a proton, the very concept of smooth, continuous space begins to gently, imperceptibly break down. It's a startling thought, isn't it? In the classical view, the one our everyday senses perceive, space is a continuous, infinitely divisible canvas. You could zoom in forever, it seems, and always find more space, more in between. Yet, quantum mechanics, with its dance of probabilities and discrete energy levels, works quite differently. And when we try to unite these two colossal theories, quantum mechanics and general relativity, theories that usually eye each other with suspicion, something truly strange begins to happen to space-time itself. According to many valiant attempts to create a theory of quantum gravity, the very fabric of space-time becomes turbulent at this Planck scale. It doesn't just sit still, it subtly fluctuates, it writhes, tiny distortions appearing and vanishing, like invisible bubbles gently rising and popping in an utterly silent, boiling water. This seething chaos, this imperceptible churning, is sometimes called quantum foam, a term coined by physicist John Wheeler back in the 1950s. Within this quantum foam, space-time is anything but calm and smooth. It's alive, teeming with temporary fluctuations in curvature, minute warps, little ephemeral loops, and momentary holes that wink into and out of existence. The geometry shifts constantly, far too quickly and far too small for any of our most sophisticated instruments to ever detect. We don't precisely know what this looks like, of course, because we haven't yet found a complete, unified theory of quantum gravity. But whatever form it takes, the implication is profound, isn't it? At the deepest, most fundamental level, space-time might not be flat or calm at all. It might be wildly alive, and within that wildness, wormholes may already quietly, perpetually exist. These wouldn't be the dramatic, cinematic wormholes you've seen in our stories. You certainly wouldn't be able to step through them, or even send a single particle. They would be incomprehensibly tiny, perhaps only a Planck length across, almost beyond our capacity to conceptualize. Yet, they would still count. They would still be real, even if only for the most fleeting, immeasurable moment. In fact, some theorists suggest that the quantum foam may be absolutely riddled with these microscopic wormholes, constantly forming and collapsing, connecting points in space that are otherwise vast distances apart. These connections wouldn't last long, perhaps only a billionth of a trillionth of a second. But if the universe allows them, it would mean that space-time is not merely dynamic, but multiply, connected at its most fundamental scales. You might need a moment to just float here with that thought. This subtle, intricate connectivity isn't something we can directly measure, not yet, anyway. Yet, it could still subtly influence how particles behave throughout the cosmos. Quantum entanglement, that spooky action at a distance, or the mysterious process of quantum tunneling, even the very structure of black hole interiors, all might be delicately shaped by the constant presence of these tiny links. The vacuum wouldn't be truly empty. It would be silently entangled, subtly curved, and quietly stitched together by wormholes, too small for us to ever perceive directly. It's important to be cautious, of course. These are still profound speculations. We don't yet have experimental access to the Planck scale, but mathematically, the idea fits with an eerie elegance. And if space-time is truly granular and chaotic at this smallest level, then wormholes might not be rare at all. They might be everywhere, all around us, woven into the very fabric of space itself. The idea that space-time might harbor these tiny, ephemeral wormholes isn't merely poetic, a beautiful thought to ponder as we drift. No, it stems from the deepest, most serious attempts to unify the fundamental laws of nature. At the very heart of this immense effort lies the search for a theory of quantum gravity, a single, coherent framework that marries the strange world of quantum mechanics with the sweeping grandeur of general relativity. This has proven incredibly difficult, a monumental challenge. Quantum mechanics, you see, is probabilistic, focused on the tiny, the uncertain, and discrete energy levels. General relativity, on the other hand, is continuous, elegantly geometric and smooth, describing the large-scale universe with perfect clarity. When you try to apply one to the domain of the other, imagine the quantum mechanics of a black hole, or the curvature of space at atomic distances. The mathematics, quite simply, breaks down. But one guiding idea has emerged again and again, like a persistent beacon in the cosmic dark. Perhaps space-time itself is not continuous. Perhaps, much like the energy levels within an atom, space is quantized, made of discrete, indivisible units. This doesn't mean there's a fixed grid or a background lattice. No, it means, as we drift further, the universe whispers secrets about its very construction, suggesting that beyond a certain colossal scale, space itself isn't a smooth, unbroken canvas. Instead, imagine it as a finely woven tapestry, a rich mosaic of tiny, discrete units of volume, meticulously stitched together by the quantum rules that govern everything. Time, too, might not be a continuous flow, but a series of infinitesimally small steps. In such a deeply textured reality, the slight foaminess we theorize at the Planck scale isn't just some cosmic side effect. It's a foundational property, the very bubbling, shifting geometry that constitutes reality's core. The gentle hum of our ship's engines is a steady, quiet companion as you contemplate this intricate, hidden world. One of the most profound ideas exploring this concept is known as loop quantum gravity. It proposes that the fabric of space-time itself is made of countless tiny loops, like quantized threads that interlace to form an immense, intricate network woven throughout the universe. These loops don't define areas and volumes with smooth, elegant curves, but through a complex, combinatorial structure, a kind of shimmering quantum scaffolding. The geometry of space, in this view, arises entirely from these connections. There's no empty backdrop for them to reside in. The network, truly, is space. Who knew space could be so intricate, even at its smallest? This perspective completely transforms our classical understanding of smooth geometry, replacing it with something profoundly textured, where general relativity paints a picture of graceful curvature and unbroken continuity. Loop quantum gravity presents us with distinct nodes and delicate links, offering an entirely new way to conceive of how 2 points in the cosmos might be connected. Within this framework, the very idea of a wormhole begins to feel more natural, not as some vast, traversable tunnel, but as a subtle shortcut across this quantum network, a direct link between distant nodes, a fold not in a physical fabric, but in the intricate structured its censorships by in, but if be in, to in with so, in well, in whereas to where ill you, to of game wix to go up by to book what I will with do I with a light car but duck what do ya to yeah to what to boy what up but what up ya the go you to if I will you put up to it if they did You feel a soft vibration through the hull, a gentle reminder of our journey. These unseen connections wouldn't manifest as visible holes. They would be utterly imperceptible to our senses, yet their presence could fundamentally alter how information travels. They might even unlock some of the stranger correlations we observe in quantum physics, explaining those patterns where particles seem to know more about each other than the vast expanse of space should ever allow. If loop quantum gravity is correct, if space is truly woven from these loops, then our universe might already be quietly teeming with these tiny shortcuts, not large enough for us to navigate, not stable enough to hold, but undeniably real, quietly, profoundly real. Then, around 2013, a truly striking idea began to emerge within the world of theoretical physics, one that forged a deep, elegant connection between two of the most enigmatic concepts in modern science, that baffling quantum phenomenon where two particles become so intimately linked that observing one instantly influences the other, regardless of the unimaginable distances separating them. And on the other, the theoretical Einstein-Rosen bridge, the famed wormhole connecting disparate regions of space-time through a hidden, unseen tunnel. Isn't that just like space, always revealing new connections? This bold proposal, simply dubbed EKR, came from physicists Juan Maldacena and Leonard Susskind. Their intuition was groundbreaking. Perhaps every pair of entangled particles isn't just correlated, but is physically joined by a minuscule wormhole, not a passage for matter to traverse, nor a gaping tunnel in space, but a geometric link, a subtle, shimmering structure embedded within space-time itself that intrinsically encodes the profound connection we perceive as entanglement. The faint starlight dancing across the console reflects the enormity of such a revelation. The evocative name EHE equals EPR draws from two monumental papers. A stands for Einstein-Rosen, referencing the theoretical bridge connecting two sheets of space. EPR represents Einstein-Podolsky-Rosen, the paradox that first questioned how entanglement could operate without violating causality. The core insight of EHE's EPR is that entanglement is geometry, that when two particles become entangled, they aren't merely correlated, they are quite literally joined. And the invisible thread that binds them is a wormhole, too small to ever see, too fleeting to ever use, yet profoundly real enough to define their intertwined relationship. This doesn't imply you could send messages faster than light, as these wormholes remain untraversable, but it suggests something far more fundamental, that space-time itself might inherently encode quantum relationships through its very shape and texture. The so-called foaminess of the vacuum, the subtle texture of quantum space, might not be a random cosmic jitter after all. Instead, it could be delicately laced with these hidden links, a network of connections reflecting the underlying fabric of entanglement beneath our every measurement. You feel a subtle shift in the ship's orientation, a gentle reminder of your own journey through this intricate cosmos. If E equals EPR proves true, then space-time isn't just a vast, smooth container for quantum fields. It emerges directly from entanglement. It is the quantum connections themselves. While this remains a powerful hypothesis, with much still unproven, it stands as one of the most thrilling ideas in modern theoretical physics. Not because it offers all the answers, but because it elegantly weaves together questions once thought entirely separate. And it leads us to a truly gentle, astonishing thought. What if wormholes aren't rare anomalies? What if they are, in fact, absolutely everywhere? If each entangled particle pair truly is connected by a tiny Einstein-Rosen bridge, and if entanglement is as ubiquitous as we now believe, then space-time itself might already be saturated with wormholes. Not the colossal, stable tunnels between stars we once dreamed of, but countless, tiny, transient structures subtly threading the universe together like unseen stitches in an infinitely woven cloth. The recycled air within the cabin feels fresh as you ponder this boundless possibility. In this captivating view, wormholes aren't oddities. They are the rule, the natural consequence of quantum connectivity. And if space-time is fundamentally composed of these connections, if its shape and form are determined by the intricate relationships between things, rather than merely their spatial locations, then wormholes might not even be things at all. Perhaps they are simply how space holds itself together, how distances acquire meaning, how order emerges from what might otherwise be chaos. We still cannot directly observe the Planck scale, so we don't yet know with certainty if this picture is correct. Yet the mathematics increasingly points us in this direction. The deeper we delve into quantum gravity, the more it seems clear that space is not just a passive backdrop for events, but an active, dynamic web. A web of hidden relationships, intricate and profound. And hidden within that vast, shimmering web, the wormholes may already be here, silently defining the very nature of reality. If these wormholes are real, even if they're minuscule, transient, or incredibly rare, then the next logical question simply presents itself. Could we detect one? Is there any conceivable way to know if the fabric of space has, for a fleeting moment, folded right in front of us? To begin to answer this, physicists have turned their attention to the phenomenon of gravitational lensing, where massive objects subtly bend, the light originating from more distant sources. Nothing to worry about, probably. It stands as one of the clearest and most beautifully confirmed predictions of general relativity. A colossal galaxy, or even an entire cluster of galaxies, can act like a cosmic lens, gently bending and magnifying the faint light from galaxies positioned far, far behind it. Sometimes, the result is a beautifully distorted arc of light, a ghostly curve stretched across the void. Other times, it forms a perfect, shimmering ring, or even multiple, duplicated images of the same distant object appearing in different locations in the night sky. This bending occurs, transforming the emptiness into a cosmic magnifying glass. And as we drift here, suspended in the velvet darkness, the console lights cast a gentle, shifting glow across your face, reflecting faintly in the viewport. You can feel the soft, rhythmic hum of the distant engines, a lullaby against the vast silence of the void, and the faint scent of recycled air reminds you of the quiet life support sustaining us. Light, you see, isn't always a straight arrow. It tends to follow the natural, curved paths woven through the fabric of space-time itself. When that fabric is warped, perhaps by the colossal mass of a star or a galaxy. Light simply curves right along with it. But what if the curvature wasn't caused by something as familiar as mass, but by a theoretical tunnel, a shortcut through the universe, a wormhole? Imagine the possibilities, the gentle sway of our ship almost mirroring the theoretical bends we're discussing. In theory, a wormhole could distort light just like a galaxy or a black hole, creating what scientists call gravitational lensing. Yet its signature, its cosmic fingerprint, would be utterly unique. The light might not just bend, it might duplicate in a way that defies comprehension. You could find yourself gazing at a star that isn't actually there, a ghostly echo of its true self, or perhaps see an entire galaxy shifted, inverted, a mirror image appearing where it shouldn't. Isn't that just like space, always finding new ways to trick your senses? Sometimes, you might even catch a fleeting flash of light from something incredibly distant, a burst that was never even aimed in our direction, but was perfectly rerouted by one of these cosmic shortcuts. Physicists have spent countless hours modeling these distortions, meticulously predicting how a wormhole's lensing patterns might differ from ordinary gravitational sources. They could appear asymmetric, subtly unstable, or warped in ways no star or black hole could ever manage. In essence, wormholes might leave optical fingerprints, distinct traces in the cosmos. We just have to teach ourselves to recognize them. And that, my friend, leads us to a truly provocative thought, doesn't it? Perhaps we've already glimpsed them. The universe outside our hull, sparkling with distant suns, is absolutely brimming with strange gravitational lenses. Some are beautifully clean and perfectly symmetrical, while others simply defy easy explanation. Odd glowing arcs, bright spots with no obvious source, lensing events that flicker or repeat in the most unexpected ways. These anomalies are rare, certainly, but they do exist, don't they? And while most can likely be attributed to overlapping celestial objects or mysterious dark matter distributions, a stubborn few remain open questions, lingering mysteries in the sky. Picture it, a slight, almost imperceptible shift in our ship's gravity as we ponder these giants. Back in 2007, a clever team of astrophysicists suggested that a particular set of double-imaged quasars, those incredibly bright, distant objects, might actually be the handiwork of a wormhole, silently bending their light. Others have even speculated that some of those elusive dark matter halos, which clearly bend light but contain no visible matter whatsoever, could be wormholes, cleverly masquerading as invisible mass. There's no definitive proof yet, no smoking gun, but the sky above us is an intricate tapestry of light, bent, curved, and twisted on its epic journey to our eager eyes. And somewhere within that maze of cosmic distortions, a wormhole could be silently hiding, a quiet echo in the fabric of reality. Of course, we must always exercise caution. Science, after all, demands more than mere imagination. It demands rigorous confirmation, meticulous replication, and the careful ruling out of other possibilities. Yet, it's not unreasonable to consider that if wormholes truly exist, even rarely, they might just leave behind a visible trace. Not a dramatic, shimmering portal, not a glowing tunnel, but something far more subtle, a delicate ripple in the paths that light takes across the cosmos, a hidden lens, a quiet echo, a tiny piece of sky that doesn't quite make sense. So, if they don't form naturally or collapse too quickly to ever be useful, could someone, somewhere, somehow, build *1? This is the fascinating realm of cosmic engineering, a kind of speculative physics that doesn't ask what we can accomplish now, but rather what might be possible for a civilization millions of years ahead of us. Imagine a society that has harnessed not just electricity and chemistry, but space-time itself. In principle, the requirements are surprisingly clear, even if the execution remains a staggering leap. To construct or even merely stabilize a wormhole, you would need to manipulate gravity with incredible precision, not just to bend it, but to shape it into an exact configuration. You'd need to control what we call negative energy, perhaps through exotic quantum fields or some mechanism we haven't even begun to discover. You would need to maintain this exotic matter in just the right distribution, continuously pushing outward against the tunnel's natural tendency to collapse inward. And you must accomplish all of this in a way that preserves stability, avoids catastrophic singularities, and keeps tidal forces within tolerable limits for any potential traveler. It's not just a question of technology, you see. It's a monumental question of energy. The scales involved are truly vast, almost beyond comprehension. Even holding open a microscopic wormhole would likely demand more energy than any civilization on Earth has ever produced in its entire history. A traversable human-scale tunnel might require the energy equivalent of an entire star, or even more, condensed and arranged in ways we can barely describe, let alone build. But if such a civilization did exist, if it had truly mastered quantum gravity, perhaps built machines the size of solar systems, and tamed forces we currently deem exotic and unreachable, then constructing or stabilizing a wormhole might not be an impossible dream. In fact, some scientists quietly speculate that if wormholes exist at all, and if they're traversable, then they may already be artifacts intentionally created rather than formed by chance. They might be the relics of a civilization that found a way to stitch space together, perhaps not for exploration or conquest, but for survival, or even for some purpose entirely beyond our current understanding. If we ever stumbled upon one, by pure accident or clever design, the next question would be even stranger, wouldn't it? Could we actually pass through it? Our ship gently rotates, turning towards a distant nebula, its faint light dancing on the control panels. Theoretical models suggest that traversing a wormhole would require unimaginable care, extreme care. The throat, that narrowest, most critical part of the tunnel, would absolutely need to be stable enough to resist collapsing around you. The traveler would have to remain meticulously within a safe zone, diligently avoiding immense tidal forces that could stretch or compress your very body beyond survivability. The internal geometry must be perfectly navigable, offering a smooth, predictable path from entrance to exit, and the two ends, the entry and exit points, would need to remain flawlessly synchronized, preventing time distortion so severe that returning to your own era becomes an impossible dream. Some models even predict intensely strong gravitational gradients within the wormhole, places where time itself slows dramatically, or space curves unpredictably around you. A person passing through could experience profound time dilation, much like near a black hole. In some scenarios, your journey might take mere seconds inside the tunnel, but years could pass outside, or, quite possibly, the reverse. Radiation might also pose a serious issue. As you moved through the wormhole, stray particles, even light, could be blue-shifted to dangerous, energetic levels, meaning robust shielding would be absolutely essential. So, imagine meticulous trajectory planning, constant field stabilization, and precise compensation for quantum effects that could destabilize the tunnel mid-transit. And even if all of that was somehow solved, if the wormhole were perfectly stable, perfectly traversable, with no harmful effects whatsoever, the simple act of stepping inside would remain an astonishing, utterly profound moment. One instant, you are here, exactly where you are now, feeling the soft vibration through the hull, the warmth of the console lights. The very next instant, you are somewhere else entirely, without having crossed the vast, intervening space. It would be a doorway, not just through distance, but through the very shape of the universe itself. Wormholes have become so familiar in our stories, haven't they? Shimmering tunnels, glowing rings, instant gateways, whisking characters across planets or entire galaxies. They hum with light, flare with energy, and promise destinations beyond our wildest dreams. ... Your ship glides silently through the cosmic velvet, the gentle hum of the engines, a steady lullaby against the vast quiet. The console lights cast a soft glow across your face, reflecting in the starlight filtering through the viewport. You've probably seen the fantastical portrayals of wormholes in old stellar projections, those swirling, roaring tunnels of light, a shortcut through the universe that announces its presence with a dramatic flourish. But the true physics, if a traversable wormhole exists, suggests something far more serene, far more subtle. It wouldn't be a visible tear in the fabric of space at all, unless something chose to enter or exit its unseen threshold. Its mouth might present itself as an ethereal sphere, simply floating, silently warping the starlight around it like an immense, unseen lens, a shimmering distortion in the black. Or, perhaps, it could be utterly dark, its presence betrayed only by the profound gravitational tug it subtly exerts on the surrounding nebulae. There would be no kaleidoscopic vortex, no thunderous roar, just the quiet breath of the void. Imagine, if you will, the passage through it, an utterly uneventful journey, much like stepping through still, cool air. No sudden acceleration, no disorienting rush. The ship's gentle vibration barely registers against the hull. You'd simply float in, and moments later, gently drift out somewhere entirely new. Time itself might play a quiet trick on you, your chronometers subtly desynchronizing, the gentle pressure of gravity, perhaps shifting ever so slightly against your seat. But no sound, no resistance, no grand cinematic spectacle, just the universe itself, subtly folded, a silent bridge of pure geometry connecting distant shores of reality. Isn't that just like space? This quiet, compelling mystery hangs in the recycled air of the ship. If these silent cosmic shortcuts are real, even nearby, why haven't we stumbled upon one? Why haven't our delicate sensors picked up any unambiguous signs? A peculiar twist in gravitational lensing, an unexpected delay in a distant pulsar's signal, duplicated images of a single galaxy, or strange distortions rippling through space-time. Perhaps, you ponder, running a finger along a cool console, they are simply too tiny, existing at scales so minute, so fundamental, that even our most sensitive gravitational wave detectors or precision telescopes would completely miss them. Imagine trying to spot a single quantum ripple in an ocean of stars. Or perhaps they are fleeting, forming and collapsing in the quantum foam of existence before even light or matter could traverse them, appearing for a breath and then vanishing without a trace. In such a scenario, they would leave behind no lasting cosmic fingerprint. Then again, what if they are simply camouflaged? A wormhole could subtly bend light and gravity in ways that perfectly mimic more ordinary objects, distant clump of dark matter, the core of a compact star, or even the vast, diffuse halo of a galaxy. Without knowing precisely what to search for, we might be observing their very signs right now, mistaking them for something far more mundane. You might need a moment to just float here, letting that thought sink in. Then there's the possibility of their rarity, relics from the universe's fiery birth, born in conditions that no longer exist. If only a handful ever formed, they could be hiding light years away, nestled behind colossal galaxies, deep within the event horizon of a black hole, or even in the vast, empty expanse between cosmic voids. And just to add a touch of cosmic intrigue, what if they were hidden by design? If a wormhole was constructed not by the silent hand of nature, but by some unseen intelligence, it might be shielded, protected, or placed precisely where it wouldn't be easily discovered. Perhaps it's locked to specific energy signatures, or visible only under unique, transient conditions. It might even exist beyond the boundaries of our conventional universe. We simply don't know. But the beautiful thing about the void you reflect as your ship makes another imperceptible course correction is that the absence of evidence is not the same as evidence of absence. The universe's silence doesn't mean they aren't there. It simply means we haven't yet learned the right language to listen. And so, the quiet, meticulous search continues, not merely through the lenses of our powerful telescopes, but deep within the elegant abstractions of theory, not just in the ancient starlight, but in the intricate dance of equations. The most honest answer to the question, do wormholes exist, remains profoundly mysterious. We don't know. Not because they've been disproven, for they haven't. Not because they break the fundamental rules of the cosmos, for in many scenarios they don't, but because the universe has not yet offered us that undeniable signal, that unmistakable pattern, that singular observation that says, without a shadow of a doubt, this is a wormhole. And yet, every profound theoretical construct we've painstakingly built on this journey, Einstein's general relativity, quantum field theory, speculative models, and our deepest cosmological observations, whispers of the possibility, not a certainty, but a quiet, tantalizing maybe. Wormholes aren't merely ideas conjured from science fiction. They are allowed solutions to Einstein's profound equations. They emerge quite naturally from the very geometry of quantum mechanics. They resonate with the strange phenomenon of entanglement. They even surface in the thermodynamics of black holes and in our most ambitious modern theories attempting to unify gravity with the quantum realm. No one has definitively proven that wormholes must exist, but crucially, no one has proven that they cannot. That quiet, balanced uncertainty alone places them among the most captivating frontiers in theoretical physics. They lie at that profound boundary, not between truth and falsehood, but between what we currently grasp and what we don't yet know how to effectively test. So, if we were to look for one carefully, patiently, without making too many assumptions, what kind of subtle clues might we hope to eventually uncover? You adjust a dial, and a distant galaxy shimmers on your main screen, its light slightly distorted by unseen forces. One possibility that has always fascinated you is the hunt for gravitational lensing anomalies. As we've discussed, wormholes could bend light in truly unusual ways, painting unexpected images across the celestial canvas, distorting distant arcs of light, or causing sudden, inexplicable shifts in brightness. By meticulously analyzing the sky, particularly in those mysterious regions where mass seems to be strangely missing or duplicated. Astronomers might just catch a fleeting glimpse of a gravitational lens that simply doesn't behave like any known object. You watch the data scroll by, a constant whisper of the universe's quiet secrets. Another powerful clue could lie in the resonant echoes of gravitational wave signals. When two colossal objects, like black holes or neutron stars, violently collide, they unleash ripples through the very fabric of space-time. These waves carry incredibly detailed information about the collision. If a wormhole were involved, either as a cosmic conduit or as a direct participant in the event, the resulting waveform might exhibit unexpected echoes, subtle time delays, or frequency shifts that diverge from our standard templates. Some researchers have even proposed carefully listening for these telltale echoes in the lingering tails of gravitational wave events. If they exist, and if they perfectly match the predicted patterns, it could offer a profound hint of exotic structures hiding in the gravitational shadows near compact objects. You can almost feel the gentle vibration through the deck plating as your ship's detectors patiently listen. And then there's the more subtle, almost philosophical idea of energy condition violations. Most forms of matter we encounter obey certain fundamental rules, like having a positive energy density. But the exotic matter theorized to sustain traversable wormholes might beautifully violate these very conditions. If we could ever find regions where energy behaves strangely, where light subtly speeds up instead of slowing down, or where radiation curves in oddly unexpected ways, it could strongly suggest the presence of these unusual space-time geometries. The ship's recycled air feels a touch cooler as you contemplate such bizarre possibilities. More profoundly still, there's the intriguing concept of entanglement patterns. If wormholes and quantum entanglement are intimately related, as the mind-bending ER equals EPR hypothesis suggests, then the intricate structure of quantum correlations might beautifully reflect the deeper connectivity of space-time itself. By studying how particles remain entangled across vast distances, especially in the context of black hole evaporation or in highly correlated quantum systems, we might learn something profoundly new about the underlying hidden geometry of space. It's like listening for a universal whisper. And finally, we could meticulously examine the peculiar motion of stars and gas. If an object orbits something that is utterly invisible, but doesn't behave like a typical black hole, it doesn't emit radiation, it doesn't seem to collapse, and it exerts truly unusual tidal forces on its celestial neighbors, it could offer a tantalizing hint, around a wormhole. You see, it's an idea that truly stretches the imagination. Glimpses of such cosmic architecture, perhaps lurking within the chaotic hearts of galaxies or cloaked by vast halos of dark matter, are not easily found. No, dear traveler, these aren't simple sightings from a comfy port. They demand an exquisite precision, an almost infinite patience, and a quiet courage to seek out what utterly defies the known. The faint hum of our engines, a soft lullaby in the recycled air, reminds us of this journey's delicate balance, the unwavering skepticism that keeps us grounded, entwined with the boundless curiosity that propels us forward. The search for these elusive cosmic shortcuts is no different. You feel a gentle, almost imperceptible shift in the ship, a whisper against the vastness. If wormholes truly exist, don't expect them to send out a grand announcement blazing across the void. Oh no. Instead, they might reveal themselves in the most subtle of ways, a peculiar warp in the path of distant starlight, an echo in the deep gravitational waves that ripple through spacetime, or correlations in energy fields that hint at something more. The console lights cast a gentle, shifting glow across your controls, illuminating the quiet readiness of our vessel. To those who have learned how to truly listen to the universe, that profound silence might not be empty at all. It could be teeming with intricate, hidden structures, simply waiting for us to perceive them. Interestingly, some of the most compelling whispers about wormholes don't originate from direct observation, but from a deeply abstract concept in theoretical physics, a beautiful riddle known as the holographic principle. Imagine, if you will, that everything happening within a three-dimensional volume of space, with all its gravity and complexity, could be perfectly described by a two-dimensional theory without gravity existing on that volume's outer boundary. It's like our entire universe could be a grand cosmic hologram, isn't it? This intriguing thought crystallized into a sophisticated framework called anti-de Sitter conformal field theory, or a DSCFT for short. In this mesmerizing ADS-CFT model, a theory of gravity operating within a specific curved spacetime known as anti-de Sitter space, with its distinctive negative cosmological constantes mathematically identical to a quantum field theory playing out on that space's outer edge. It's a strange and utterly captivating notion, isn't it? It suggests that the very fabric of spacetime, along with gravity itself, might not be fundamental, but could actually emerge from something purely quantum and lower dimensional. And here's the most remarkable part, the one that makes your breath catch. Wormholes, those wondrous shortcuts, appear quite naturally within this very framework. Within some of these holographic blueprints, a wormhole linking to black holes in the bulk space directly corresponds to a state of profound quantum entanglement between two systems residing on the boundary. Think of it, the wormhole isn't just permitted, it's demanded by the structure of entanglement itself. If these two distant sides are maximally entangled, the geometry absolutely must include a connecting bridge. This lends profound mathematical weight to the idea known as E equals EPR, dazzling proposal that entanglement isn't merely a shared behavior, but a kind of cosmic glue, intimately weaving spacetime together. The wormhole, in this instance, isn't a tunnel you could traverse. It's a living manifestation of quantum relationships. You might need a moment to just float here and ponder that. Now, our own cosmos, the one we're quietly drifting through, doesn't quite fit the anti-de Sitter mold. It possesses a positive cosmological constant, not a negative one. Yet, many brilliant minds believe that the profound insights gleaned from a DSCFT might still hold true for our universe, at least as a powerful approximation. The holographic principle, even if not a perfect fit, could be a guiding star, illuminating the path toward a deeper, more fundamental theory. A theory where geometry, gravity, and even the connectivity of everything we see and if that's the case, then wormholes might be whispering something truly fundamental to us. Not about space as we currently perceive it, but about space as it emerges. The faint engine hum is a constant reminder of our journey deeper into these mysteries. To explore this further, we gently turn our attention back to black holes. Black holes, nature's most extreme laboratories of gravity and quantum mechanics. These cosmic behemoths twist the very fabric of spacetime so intensely that absolutely nothing, not even the fleetest light, can escape their grasp once it crosses the event horizon. You can almost feel the pull from the distant, unseen giants out there. But their very existence poses incredibly difficult questions, don't they? What truly happens to all the information that plunges into one? Does it simply vanish, thereby shattering the very laws of quantum mechanics? Or is it somehow preserved, perhaps encoded subtly on the surface, or released much later through some delicate form of radiation? These profound riddles lie at the very heart of the black hole information paradox, and the quest for answers has led to some truly startling conclusions. Why does the universe always do this to you? Just when you think you understand. In some of the most daring theoretical scenarios, the interior of a black hole isn't a dead end at all. Instead, it might be intimately connected to another region of spacetime, a strange mirror image, or perhaps even another universe entirely. Isn't that just like space? To hide such wonders within its deepest shadows. These models often conjure up wormhole-like geometries, where the terrifying singularity at the center is cleverly bypassed or even replaced through exotic shifts in topology. One fascinating idea suggests that the two ends of a wormhole could correspond to a pair of entangled black holes, their interiors joined by a bridge that, while perhaps impassable, still plays a crucial role in safeguarding quantum information. Another proposes that even black holes in the process of evaporating might maintain a hidden, intricate structure deep within a lingering imprint of every particle and field that ever tumbled inside. In either case, the very topology of spacetime, its global structure, its hidden folds, its intricate connections, becomes absolutely central, not just for comprehending gravity's might, but for understanding how reality itself stores and processes information. Wormholes, in this light, are far more than mere tunnels through the cosmos. They are complex architectures of information flow, perhaps representing the universe's own ingenious methods of keeping track of itself, even when its constituent parts seem utterly cut off or irrevocably lost. We cannot directly see these subtle topologies, of course, yet through the profound insights of black hole thermodynamics, the elegance of holographic dualities, and sophisticated mathematical models, we begin to catch shimmering glimpses of their intricate outlines. And within those outlines, wormholes consistently reappear, quiet, persistent, and deeply strange. All of this, from the mind-bending E=EPR concept to the complexities of loop quantum gravity, and even the theoretical energies required to stabilize a traversable wormhole, rests upon a profoundly delicate balance. It's the constant tug-of-war between theoretical possibility and observable reality. Physics, you see, has always lived at this precise edge. Equations can be exquisitely beautiful, internally consistent, even remarkably predictive, but until nature itself gives a resounding yes, they remain, in essence, conjecture. A theory, after all, isn't a truth. It's a question, phrased in the most elegant language of mathematics. With wormholes, this tension feels especially sharp. The math absolutely allows for them. These frameworks, beautiful and complex, strongly suggest their existence. Quantum theory and our understanding of gravity keep pointing towards these tantalizing hidden connections. Yet no telescope, however powerful, has ever definitively spied one. No detector has confirmed their subtle influence. No spacecraft has ever accidentally or intentionally tumbled into a tunnel that cuts through the cosmos. This absence of direct evidence, you understand, doesn't automatically mean they're false, but it does mean we must proceed with an immense amount of care, moving slowly through the gentle drift of our ship. The true danger isn't in dreaming too grandly. No, never that. It's in mistaking a beautiful dream for a confirmed discovery. Physicists, bless their relentless curiosity, continue to labor on both sides of this fascinating divide. Some push the mathematical boundaries even further, exploring what wormholes might look like in universes with entirely different fundamental constants or under wildly varying boundary conditions. Others gaze skyward, refining their models, developing breathtaking new instruments, perpetually searching for signals that simply don't match any known source. Both approaches are vital, aren't they? Together, in this quiet, shared pursuit, they help us gently feel out that elusive edge where pure possibility finally meets the undeniable fabric of nature, where today's wild speculation might, just might, blossom into tomorrow's indisputable data. The recycled air around you feels charged with this potential. And even if, in the vast expanse of time, wormholes are never definitively found, the very path we've taken toward them teaches us something incredibly valuable. It's a quiet reminder that not every profound mystery is meant to be solved quickly or even fully within our lifetime. Some exist solely to widen the scope of our thinking, to stretch the very boundaries of what we believe space and time are truly capable of. They invite us to truly